Well, this is more of a technical talk, but partly inspired by the fact that UFO reports frequently discuss impressive maneuverability with usually no indication of conventionally known drives. And to cut to the chase, just in case I should run out of time, a sufficiently advanced technology can use antimatter annihilation to power a reaction drive whose only exhaust is an intense beam of neutrinos. This would not be visible. It would be very hard to detect by any means, but it is potentially a testable hypothesis from retrospective evidence that already exists. Just as a note, by a sufficiently advanced technology, I mean something that can accomplish anything that can be that is known to be physically possible, but that does not require any new physics, simply on the grounds that I felt that a hypothesis is more credible if it sticks to things that we know are possible in principle. Now, there's been a fair amount of discussion about theoretical space propulsion. At the moment, the only physics we know of relevant to space propulsion involves a law of equal action and reaction. The only way you can move in one direction is to throw something else, reaction mass as I call it, in the other direction. There are some variations that basically involve getting your reaction mass from outside the vehicle, but they still adhere to Newton's third law. And the most powerful known reaction drive is an antimatter rocket. I was told after I submitted my abstract that it would be good to provide a brief primer on what antimatter is to begin with. So every type of particle making up normal matter has a corresponding antiparticle. The relation between antimatter and normal matter is that every measurable property is either identical or exactly the opposite between the two. Mass is one of the identical properties. Antimatter particles have the same mass as matter particles. Electrical charge is one of the reversed properties. The anti-electron is also called the positron because it has a positive charge. The antiproton has a negative charge. When matter and antimatter meet, they annihilate, releasing energy. And just historically, the first antiparticle discovered was the anti-electron or positron. Okay. Now, electron-positron annihilation is nice and simple. They simply meet each other and convert into a pair of gamma rays carrying all of the energy. Now, in accelerators, we've been studying antiprotons for decades now. Their annihilation is more complicated, partly because a proton is a composite object made of 3 quarks. An antiproton, of course, is made of 3 antiquarks. And partly because the energy release is so much bigger that completely new particles, or rather particle-antiparticle pairs, can be created out of the energy. This is a reversible process, but there is no material particle lighter than the electron, so there's no alternative but photons here. The primary annihilation gives you a mess of unstable reaction products that ultimately are all going to decay or mutually annihilate into photons and neutrinos. Now, if a single antiproton annihilates inside a large nucleus, most of the intermediate products are strongly interacting mesons, which are very efficient at transferring energy to the rest of the nucleus. So aside from photons, most of the energy appears as thermal excitation in a nucleus that's literally been blown apart by the excess energy. However, if an antiproton annihilates an isolated proton, the ultimate products all break down into photons and neutrinos, and the neutrinos end up with the lion's share of the energy for technical reasons that I can get into later on if anybody's really interested. Now, for a reaction drive, the faster you throw away your reaction mass, the more efficient your drive is, the more thrust you get per unit of fuel you're using up. The ultimate reaction drive would have an exhaust velocity equal to the speed of light. Now, which essentially amounts to turning your fuel mass into radiation and beaming it out the back. You might think that you can do that with antimatter, since it annihilates matter completely into energy, except that the aforementioned neutrino problem, the neutrinos fly off in all directions equally. You can't direct them. You can't manipulate them. So much of the energy is lost in terms of neutrinos that a rich mix antimatter rocket would actually be terribly inefficient. But that assumes you're just burning the matter-antimatter mix in a reaction chamber. The trick is to pre-accelerate the particles you're going to annihilate. As in a particle accelerator on Earth, you accelerate both the proton and the antiproton to high speed, but in the same direction, not ramming them into each other the way we do for experiments. They annihilate at high speed. The reaction products inherit that center of mass motion, and then you put in a retrieval stage. The stuff that you can interact with, you capture, reprocess the energy, use it to power the acceleration for the next particle pair. Meanwhile, the neutrinos escape. All of the momentum that has been put into them by the pre-acceleration is just carried out of the chamber, and you get a net thrust. I'm going to skip quickly over the math here. We can refer to it in question and answer if people really want. But this graphic illustrates the drive attributes in a perhaps somewhat more accessible way. Down here at the bottom, I've plotted the fraction of retrievable energy, the amount of annihilation energy that can be captured and used. And that actually depends on how big your engine is and how much free path you have for intermediate reaction products to decay. If something is still a pion of some sort, you can intercept it and use it. It will decay naturally into neutrinos and photons, and that's where those neutrinos come from. It's a process that takes time and requires a certain amount of free path to be completed. Now, fortunately, the math on the previous page indicates that the higher the mass retention, that is, the fewer neutrino decays you allow, the higher your effective exhaust velocity, the amount of thrust you get per unit of fuel. This is a good thing because that means that the smaller your engine, the more powerful and efficient it can be. Just for comparison, a lean mix antimatter rocket where you're doing simple a burning-like effect and have perhaps 5% antimatter would have about this thrust to mass ratio. An ideal fusion rocket would be down here. An ideal fission rocket would be down here. And the chemical rockets that we're actually building nowadays would be so far down into the corner that there's no room for the font. Now, what that means in terms of the performance of such a drive system, oh, sorry, I overshot. This shaded area here shows the approximate regime for an engine of reasonable size, a few meters across, and you can see that our effective exhaust velocity is indeed very close to the ultimate possible limit. A vehicle with a drive of this type, if it made a constant 1g thrust trip from the moon to the Earth, it would use up 0.42 kilograms of fuel mass for each metric ton of vehicle mass. That's about 1 pound of fuel, an eighth of a gallon to fly your car from the moon to the Earth. If a vehicle had a 1-to-1 mass ratio, meaning that the fuel tank holds as much as the payload. It could thrust at 1g continuously for 245 days. This is the kind of figure people are talking about for interstellar travel by conventional means through normal space. Whatever we might think about interstellar travel, this obviously gives us ample power for maneuvering and travel within the solar system. So, in terms of empirical consequences, detecting neutrinos is extremely difficult, but there have been neutrino detectors in operation. Some of them are actually being called neutrino telescopes these days because they detect astronomical events, literally for decades. They had already established a solar neutrino problem in the late 1970s. Now, most of the output of a neutrino drive will be muon neutrinos because those are produced by the first step in the decay cascade, and we recall that you want to keep the decay cascade short because that's what makes the drive more efficient. However, the solution to the solar neutrino problem that I mentioned a moment ago is that neutrinos oscillate. They change identity. Muon neutrinos will, over a sufficiently long flight path, some fraction of them will transform into electron neutrinos, which can be picked up by the detectors. So this postulates the possibility of a very simple retrospective test for whether vehicles that we see do, or that we think we see doing violent maneuvers in Earth's atmosphere are being powered by neutrino drives. Simply plot the direction of the maneuvers in three-dimensional space, note what direction they're accelerating in, plot the opposite direction, ignoring trivial obstacles like a few thousand miles of rock, and see if they intersect a neutrino telescope. If they do, consult their records and find out if they got a blip of neutrino events at the appropriate time. I have no idea how such a test would come out, but at least it's a test that's doable. There are also some more practical consequences. Antimatter is a tremendously rich energy storage system. There is a lot of stored energy in such a drive, E equals mc squared. A vehicle that crashes, or even just loses whatever its containment system is going to explode with a great deal of power. Even a kilogram of or so of antimatter is going to be a multi-megaton blast. Among other things, this means that shooting them down doesn't sound like a very good idea if they're using this drive. Offhand, the only way I can think of to avoid a tremendous explosion upon crash landing is if the vehicle has already run out of fuel, which, when you think about it, is a pretty good reason for a crash landing to happen. Just as a note for possible implications, there's still speculation about what the Tunguska explosion in 1908 was, but the estimated power of the blast would correspond to the amount of antimatter that would power a small vehicle for a few hours of high G maneuvering. So if one can only imagine what a large vehicle powered for more than a few hours of maneuvers would produce if something bad happened. So that brings me to the end of my talk, and I'm happy to answer questions.
A couple of questions.
Mm-hmm.
So just a detail first. You talked about efficiency improvement from the 30% to more by pre-accelerating the matter-antimatter mix. But from conservation of momentum, it would seem that whatever you gain from the increase by pre-accelerating, you've lost by doing the pre-accelerating. Let me just add something to this, and then I'll get off the microphone. Second thing related is that if we are to believe the UFO sightings, these spaceships can make right-angle turns and so on. So any sort of immense acceleration from any sort of inertial accelerator would slam the poor inhabitants of the spaceship against the wall with tremendous velocity. Therefore, it seems like some sort of drive would have to turn off inertia rather than use it. And then finally, given what you've talked about with this very efficient drive, how about looking for a new green technology?
Okay, to address those points one after another, what happens with the pre-acceleration is that because the neutrinos escape, the portion of the imparted momentum that corresponds to their share of the total mass energy just leaves the system. That's how you get thrust. In terms of protection against high G maneuvers, okay, geometrically there's no such thing as a right-angle turn. It may require enormous acceleration, but there is going to be some acceleration involved. Writing about ways to protect against high accelerations is another issue, but in principle, we think we can already imagine ways to shield human astronauts from accelerations up to 100 G or so. We are missing some of the chemical and biochemical technology for that, but it seems to be a solvable problem. And I did not want to try to branch into too many areas of technology. In terms of a green technology, antimatter has the drawback that it is a secondary fuel source. It is a storage system rather than a power generation system.
Okay, Bernie, and then we'll go to that side of the room.
I'm a little surprised to hear you say that the most efficient form of propulsion is by having very high exhaust velocity, but the ratio of the momentum to the energy goes as the inverse of the velocity, which is the opposite of what you want.
The most efficient, okay, here I am casting efficiency in terms of how much delta V can you get for a certain mass of fuel. The higher your exhaust velocity, the less mass you use up, but the more energy you expend. And this is simply a fact of life about the way reaction drives work.
And the second question goes back to what Garrett alluded to, that the reason you're getting the neutrinos to go out in one direction, the direction that you want, is because you're pre-accelerating the antimatter. Mm-hmm. And so you've just transferred the acceleration process to the antimatter acceleration. So there you have the same problem of not being able to get around Newton's third law.
The whole point here is to work with Newton's third law. If you had a fuel lump and you simply shook it back and forth, accelerated it, and then caught it and stopped it, you would get nowhere. Because you can use this annihilation transformation to convert part of it into a form that simply escapes out the back, the amount of thrust you produce in the acceleration phase is not completely neutralized by the catching process where you intercept the portion of the energy that still interacts with normal matter. Then you're using that energy to accelerate the next lump in the train. In a realistic system, this would be a continuous process, but thinking of it as a sequence makes the concepts a bit easier to follow.
Okay, if Stoyan Zarg is in the room, can you start coming up? Okay. And Dale Graff?
Yes, a question. I think this summer we'll learn a little bit more about what went on at Tunguska when the Italian team digs down into that lake to find out whether or not it was from a comet that hit or not. So I look forward to seeing that result. I have a comment on the propulsion thing here. Neutrinos are really tough to detect, and the detectors I'm aware of that are deep in mountains only catch a few hits a year. So maybe there's going to be a change in the technology that might help increase that hit rate. And you might want to comment on that. And the third comment I'd like to make is cosmologists do a lot of talk about 80 or so, 90% of the universe, I think it's 96% of the universe being dark matter. Is there any theoretical work done on how we might be able to capture dark matter?
Okay, I love these multi-part questions. I am not trying to make a case that the Tunguska blast was an antimatter explosion. I simply wished to point to it as an example of the type of event we're looking at. In terms of neutrino detection, that is constrained by particle interaction cross-sections, which at the moment we have no idea how to manipulate, and there may in fact be no way, even in principle, to manipulate them. I'm sorry, but I managed to lose the third part of the question. Dark matter. We don't know what dark matter is, but whatever it is, it presumably shares the properties of neutrinos in having very low interaction cross-sections. Therefore, being able to tap it for energy looks like an exceedingly remote prospect at this time.
I always bend the rules a little bit when younger people want to participate, so we have one more question.
I was wondering how you would capture those particles to reuse them to get energy to use the other particles for more energy. Does that make sense?
Okay, how do we actually do the capture and reprocessing that I refer to so glibly? The answer is that this is where I wave my hands with the phrase of sufficiently advanced technology. We know that it's physically possible in principle. We don't know how to actually build the machine, or we'd be flying these things right now.